Hello everyone, it's Anvit Kumar. Welcome to Key Concepts. In today's session, we are going to continue the motor tuning sessions. And in today's session, we are going to see you like what are the different criteria to select the ISD threshold values. Before starting the today's session, let's see what are the key points that we have discussed in our last two lectures. That's actually it's related to this one. So if you not watch this video, please go to the I button, or you can find in the playlist. So in last session, what we have discussed, like initially there's one video we have discussed like what is the need of motor tuning. So that's a general question always comes in mind. So more or less I got this question like why we need to tune each and every motors whenever we design. So what actually happens if you design any motors like the electrical parameters of the motor is totally it might be same, it might be different. In most of cases it totally different. So resistance, inductance and motor velocity constant values are totally be different. So we are not like say we can't keep each and every data as parallel to like match with the previous motor. So each and every time when we have a design new motors, we have to select you can say the motor tuning parameter that will support that motor, and that's more or less related to the performance of the motor, how actually you want the device to run or motor to run to get your desired performance. So that's the reason why we need to tune each and every individual motor. So there is one more confusion with the very much like so many persons ask this question like if you have a like one motors once you design, and if you go to the mass production of the 100 motor or 1000 motor or 200 like more quantity, if you go to the mass production, is this how we going to tune each and every motors? So answer is no. If you design one motor and if it's like perfectly tuned with your device, like whatever the device you have selected, and if you're going for the same motor for the mass production, you don't need to tune again and again. Once you're done with the fine tuning, then for the same motor parameter, for the same designs, the same binding data, and the same wire gauge, same magnetization, as we can say the whatever the electrical parameter as you design first motor, if you are keeping the all technical parameters with the rest of your mass production motors, you don't need to tune your device. That will work perfectly with the rest of your motor. Some cases, some tolerance comes in a figure, so you need to for that also just take some example. Like if your motor is running like some motor, if you design like some resistance like 2 ohm and inductance value are going to get like 5 millihenry, and the motor velocity constant value is 420 millivolt per hertz. And some if you go for the mass production, sometime binding once you bind with some automatic binding machine, sometime layering section is improper due to some manufacturing you can say issues. Sometime parameters may vary, but how much vary that depends. So 10% tolerance is acceptable. So if you can say like 2 ohms, so you take a 10% of that particular resistance, the same with the rest of whatever the parameters there. If you're going to take 10 to 15% tolerance, it is acceptable by mode of the devices. If the tolerance is higher, then it might be a problem. So you need to tune your motor in such a way that your rest of the motor will work fine with that. And the another point that we have discussed how to find or measure these motor parameters like motor resistance, motor inductance, and KT values. Okay, or a back EMF constant values, or a motor velocity constant value. So all those details that I have discussed in our last lecture. If you didn't watch it, please go and watch that video. Then only please try to continue this one. So in today's session, we are going to start with the before startup setting. So this is actually you can say the sequence that we need to follow, and also the motor startup algorithm work in this same sequential manner. So before startup setting, then it will go to the PSD position state detection, and next then it will find the way, then it will go to the startup setting. So we are covering all those you can say the blocks individually and very brief way. So let's start with today's session. So the first question always comes in our mind, like what is the ISD actually stands for, and how we need to select these value. What is the need of these values to need to select? So ISD basically stand for initial state detection. Initial state detection, it means, as you can see, the state detection. State detection, it means like whenever the you can say the motor starts to operate, we need to find the motor state. So which state it is. So there are two different states. Either the first possibility, the motor is running, like it will spinning or running, and the another consider the another, you can say, the point, it may be possible it's in a stationary condition, right? So if the motor is in a running condition, what you need to do, if the device is find the motor is running, so how it's going to do, and how it justify motor is running, and the any motor is stationary, how this device will justify that point ki motor is running or still is in a stationary condition. So what we usually have, we have two face-to-face comparators. Comparators, as you might aware of that, it's going to compare the two different phases. Like if you say there are three phases in our motors, so how it will work? Let's see some basic about this parameter. So we have some phase. Let's consume, like let's name it U. This one is V, and this one is W. Okay, we have one comparator which will be like between these U and V. Okay, so I'm just trying to connect it. So we always take this one as a reference, so positive, negative. Let's assume some condition where the motor is spinning, and some waveform like motor sinusoidal waves is a sine wave motor, we are actually assuming it. So it's a sine wave, and in some cases like it has some, you can say, leading by some angle, you can say 60 degree. Let's assume some case. So if we compare these two, you can see the graphs, we are going to see that 60 degree difference in the whatever the resultant sinusoidal waveform is coming. Okay, the same way we are connecting this one. Okay, and there's one more comparator that we have, and you can say, sorry, so positive, negative. So we are considering U as a reference. So if the still motor is running, the same way it's also have some sine wave. Okay, and let's assume it's lagging by some angle. Okay, so in the same way you are going to get the whatever the, let's assume 30 degrees, so you are going to get the 30 degree difference in the output. So whenever your motor is running, still running, it's running, it's spinning, it's still spinning, in that time you are going to get these phases, because motor is not in a stationary condition. You are going to get some phase differences, and based on that phase differences, motor this ISD setting knows the motor is still running. In that time motor is directly going for your motor startup setting. Okay, that we are going to discuss in our next few lectures. So please understand, when the motor is running in forward direction on a reverse direction, it will go to the directly startup setting. If motor is stationary, it will execute first, you can say, the ISD or PSD setting, and then it will go for this, then it will go for the, you can say, the startup setting. Okay, this is the sequence how these devices. So the common doubt comes in our mind, like spinning, what actually it means. Let's assume you on the motor. Okay, it's running, and again just it's running for some RPM, certain like 350 RPM, and the same time you just switch off the motor. Okay, assume some condition where the motor is not still in a rest condition, it's still rotating, right? It's not stopped still. In that time, if you on the device or on the power supply, the motor will first find these phase differences, whatever the point I have discussed, and based on that, if it's still motor is running, but it's like we off the motor, again you switch on the motor, but the motor is still running, it means that you are going to get the phase differences, and directly in that case it will directly execute as the same point. As you can see, that this is the sequence what we have follow. So if the motor is the startup section is this, then if your motor is still a running condition, directly jump to this one. If not, then we follow this sequence and then its sequence. So okay, and the another condition, if you are having a motor and the motor is in a stationary condition, and if it is a stationary condition, so what actually happens in that case, you are not going to get. So if see the waveform of this one, it will going to, there is no motor operation, so whatever there is no, like you can say the current is, there is no waveform in the same way there is no waveform here, so resultant the difference going to get 0. The same way also here the difference is 0. So we assume that when the phase difference is there, then motor is running. We not need to process for the PSD setting, and if your motor is getting 0 phase difference, then it going to proceed for the PSD setting, then it will have to go for startup setting. Hope you get the clear idea. Okay, now the first, like we have discussed what is the need of this one and how it's working. The next point comes in our mind, like what are the criterias when we need to select these values, or how we select these values. Okay, so there are two major, you can see the different like criteria in which we need to select the motor velocity constant value. The first is motor velocity constant. The motor velocity constant is the one factor. Another is inertia, which is like motor inertia, like how heavy your motor, whatever the load you have put on it. So depends on these two factors, we need to select different like initial speed detect threshold values. Okay, and this is the mostly value comes in like it's always been a second, okay, or a millisecond, or in frequency. So it's always be in a time as well as the frequency. Okay, so some devices use time as a reference, like for parameter defined definition, and sometimes they use frequency. So we will see both concerns. Okay, so theoretically, if we see that like the motor having, we can say usually if the motor having very high inertia, you can say like usually we select very higher time, or a threshold value is higher, and in the case of time, and in the case of frequency it's very less. Okay, so theoretically what is our presumption, like always try to get the as higher possible values, if the time as possible higher, so it will help motor to resynchronize the motor at a lower speed. Okay, let's see it in a detail. Okay, let's assume the motor is in a stationary condition. So if your motor is in a stationary condition, so like we have some graphs, just try to, let's assume the motor is in a, you can say the stop condition. So what happened in that time, let's consider like when you switch on the device in that time. Okay, it will wait for this particular time, like once you have your motor, like you have selected the ISD value is 1.2 second, or some whatever the value they have provide the manufacturers. Okay, so it will wait for this particular time duration, and then it will send the ISD setting, or like whatever the PSD and PSD and settings, they will it will initialize the motor, and then it will go for the startup setting section. Okay, so this one is ISD, this one is PSD, and this one is startup. Okay, so how you define your whole tuning in a graph. This one is actually a single phase current waveform. Okay, so what I'm discussing, okay, so this is the time between when your motor stops. This is the time duration when your motor stops and the next starts. The things I have discussed. The keep enable the initial speed detection checker checked all the time when the IC is power up. Whenever the IC is power up, it will always check the state. If it will find that motor is in a stop condition, it will initiate the PSD setting, and then it will go for the startup setting. If it finds the motor is running, then it will always work in the startup setting section, whatever the settings that you have made. Okay, to avoid the waiting time, if you have selected perfectly value, then it will avoid the waiting time where the motor is still in a running condition, and it will start for the motor is still spinning condition, then it will directly start from that point. You don't need to wait for the stop and then you have to start for. Okay, When your fan is at the same point I have discussed, if your device is if your fan is like in a stationary condition or motor is in a stationary condition, you're not going to get any zero crossing value. And if you're not going to get any zero crossing value, it means that your device is in a like a stationary condition. And how are you going to find? We already watched that we have some comparators. So based on comparators, we compare the phase differences, and we have decided whether it's if we are going to get any phase difference like in a back EMF, then we presume that the motor is in a running condition. If it's not coming, then we presume that the motor is in a stationary condition. So if it is running a stationary condition, they have to go for the ISD or a lies and go startup setting, and we will start the motor accordingly. Okay, same point. So this is the when your motor is in stop condition, how it's going to initiate the PSD setting, and then it will go with the this one. And if you go, if this is a graph when the current waveform when your motor is in a running condition. Okay, now see what is the when the how it will work when the motor is in a running condition. If the phase comparator have a different motor phase difference, if a back EMF value have a phase difference, then it will presume that the motor is in a running condition. The same point way that we have discussed. Okay. Okay. So this is the graph. This is the graph that you are going to get when when you switch off the motor, like when the current waveform is coming, and certainly switch off the motor, so it will stop. Okay. So this is the condition when the motor is a start without PSD or ISD. Let's assume some, you can say the graph, some condition like still motor is in a running condition, it's not comes in the rest, but device is such turned off, then suddenly you turn off or turn on the design, it will directly start with this setting. So this one is basically a startup setting. This is basically a startup setting. This is basically a startup setting. Okay, it will not initiate any PSD setting. So let's in a details, let's see in this points in a detail. So okay, so what we have, this one we have just switch off the motor, it will try it for some concern, and it will in a run, still the device is motor is not stopped, it's still running. So it will, after some very small time duration, it will try it, and it will directly go to the startup setting. It will not go for PSD setting, it's because the motor is still running. Till now you might get a very brief idea about how these ISD settings work. Let's come to the selection criteria. Okay, as we have discussed earlier, like there are two different criteria to select these values. First is velocity constant, motor velocity constant value, that is in short KT value, and another criteria is like motor inertia. So let's see these all selection criteria separately. However, a motor with the lower velocity constant have always we have a lower you can say the velocity constant or back EMF value at a lower speed. Okay, so it is to get a proper triggering, we need to select the lower time or a higher frequency to perfectly resynchronize the motor or to start the motor. Okay, if we have a, you can say the back EMF value is not sufficient, then we are not able to perfectly start the motor. So in that case, if your motor having a lower velocity constant value, please always try to take lower time or a higher frequency. Okay, in the same way, a vice versa case, if your motor having a very high velocity constant, in that time you need to select the higher time, so it will it will easily detect the, you can say the back EMF, because if your motor having very high velocity constant at the lowest speed itself, it has a very good back EMF value, so it's not very hard to sense the back EMF value. So if you select the very high, if you select the higher time, it will very easy to select the it easy to start the motor. So in the very higher velocity constant value, we need to select the higher time or a lower frequency. Okay, so this is some guideline that some manufacturers give, so I just taken some reference, and also I use my own experience for that. For like if you have a motor velocity constant 90 millivolt per hertz, just try to go with 80 to 800 millisecond, and if your frequency, it's always try to go in the range of 0.8 hertz, And this is the I have tuned some motors like 12 volt, like you can say a table fan. So I selected these values. If you have a velocity constant of 450 volt per hertz, you always try to go select the value in the range of seconds, like time duration will be in a second, and the TSD threshold frequency will be in the, you can say, 0.16 hertz. And ceiling fan, that's the two criteria that I, based on my observation, I just set the data. Another thing, the motor with the KT value is greater than 1 volt per hertz. We always try to take the 0.8 hertz. This is also some manufacturer given some guideline. So more or less, some companies or manufacturer, IC manufacturer, they give some guidelines. So you need to follow that. So that depends. But basic idea, whatever the point that I have discussed, this is the whole idea. Like the getter KT, if you have a KT value is higher, please try to get the higher, and you can say the ISDT threshold value. It means that in the case of time, okay, so it's a lower frequency. And the same way in the vice versa case, if your back EMF constant value is less, in that time you have to select the, you can say the less time duration, and the same way frequency is higher. Okay. The next criteria, that if your motor having a higher, you can say the motor inertia, inertia actually tendency to get the motor to keep moving or existing constant value, or keep it in a still. The same way, like we have already studied in Newton's law, that what is the meaning of inertia. Inertia actually tendency of any device to keep is a state. Okay, if you're moving, so you always try to be in a condition of like the moving condition. If you're in a stationary condition, always try to keep in a stationary condition. So the motor inertia depends on the motor structure, includes blades. So usually the motor blade having like very high, heavier blade or a larger blade have a greater inertia. Okay. Okay, so inertia, like it's all about the weight, how much it has. So okay, so some manufacturers, they might define the inertia value. Most of cases they didn't provide you this information, so it's very difficult. If you are by manually, if you are going to calculate, it's really very difficult, and definitely you are not going to get very much, you can say, the accurate data. So what's the way out for that? Like how we define the motor having a higher inertia or a lesser, like you can say the less inertia. So what usually we do, we use some DSO, okay, and we connect these two phases to the motor and rotate it in a when it's connected with the load, or like you can say the blade and everything is assembled. When you rotate it, then what we have, if the back EMF value, whatever we are going to get, if the back EMF value is time period of that particular oscillation, like a sinusoidal wave, is higher, then we understand that the motor having the higher, you can say the motor inertia. Okay, so motor inertia affects the alias time, and alias time, it means like when we discuss in our next session, like how the motor starts in a PSD. As we know that the motor, the PSD settings are usually used when the motor is not permitted to go back. Okay, so we need to send some high frequency in it, and then we select like know the exact position of our rotors where actually it parks, and based on that we select some sufficient current to inject in it, and once we inject a sufficient current, the motor will start from the forward direction, it will not go back. In the alias and go condition, we always, in the algorithm itself, we select some random value, send it to the device. Depends on the open loop current how much you have selected, and inject that current to the motor, or in some cases they have alias time or open loop, you can see the current time. So based on that current only, you need to send that current, and in that time motor will go back or forward, sometime go back, and first alias and then it will go. So this is the whole value depends. So higher motor inertia, we need to select the open loop current value higher, or inertia with the alias time value will be higher. So the greater inertia means longer alias time and longer IST time. So in summary, this is the whole, you can say, the understanding about the parameter. So just for summary, so if your motor having higher inertia, please try to select the higher, you can say the longer time duration. If your motor having a lesser inertia, please try to select the lesser or smaller time. Thanks for watching my video. Please follow the session, because the next session I'm going to discuss about the PSD setting. That is that's also very much you can say the very important one. And if you have any doubt related to this particular setting, please do comment below. I will, if I find a very good question on it, I will try to make separate video, okay, or I will discuss the your doubts in a next video, like for in our first revision section. And thanks for watching the video. Please, if you're not subscribed my channel, please go through it. I always try to convey very useful information in this channel.